This is the beginning of P3, the applications of physics. Within this series of tutorials, we're going to look over all of the major aspects of P3, from the applications of physics through medical physics, onto collisions and kinetic gases. Within this first tutorial, we will look at an overview of radiation, ionization, and some of the basic applications of physics within medicine. So we will make sure that we can understand a range of methods used by medical physicists to help doctors. We will look at how radiation intensity is affected by distance as well as the medium it's travelling through, and we will look at how to calculate radiation intensity. We will start by looking at some of the ways that physicists have helped to move medicine forward, from the use of X-rays to look at broken bones, to CAT scans to enable us to examine the brain. So what is medical physics? Well, medical physics is any part of medicine which uses physics in order to investigate a condition or a disease. For example, CAT scans, which use electrons in order to examine the brain. Ultrasound, which uses ultrasound frequencies in order to generate an image of the unborn fetus. Endoscopes, which use a small camera in order to examine inside the person's body, for example in the throat. And radiotherapy, which uses radiation and radioactive elements in order to treat cancers. So, what do we mean by radiation? Well, radiation refers to any form of energy originating from a source, and can be sorted into one of two types. The first type is in the form of a wave. For example, the radiation that is emitted by our sun. This is known as gamma radiation. The second type is in the form of a particle. There are two types of radioactive particle that we need to know. The first of these particles is the alpha particle. An alpha particle is very similar to the nucleus of helium in that it contains 2 protons and 2 neutrons. However, it does not have any electrons. The second of these particles is the beta particle. This beta particle is a high energy, high-speed electron that has been emitted by certain types of radioactive nuclei, for example potassium-40. This production of beta particles is known as beta decay. We will look at alpha, beta and gamma radiation in more detail over the next couple of slides. We will now look at the 3 major types of radiation in more detail. First of all, we will look at alpha radiation. On the previous slide, we looked at what an alpha particle was. We looked at how alpha particles are made up of 2 protons and 2 neutrons. This means that when a nucleus emits an alpha particle, it will lose 2 protons, so its atomic number will decrease by 2. Due to this decrease in atomic number, the element will go through a change and become a new element. This new element will have a new atomic number, which will be 2 less than the previous element. It will also have an atomic mass of 4 less than the previous element due to the loss of 2 neutrons along with the 2 protons, making a loss of 4 particles overall. We will now look at a popular examination example, the example of Americium 241, which is an alpha emitting source used in smoke detectors. In this example, Americium 241 has an atomic number of 95 and an atomic mass of 241. It will undergo alpha decay to form Neptunium 237, which has an atomic number of 93 and an atomic mass of 237. As we can see, an alpha particle of atomic mass 4 and atomic number 2 has been released. Finally, some important facts about alpha radiation. Alpha decay only occurs in very heavy elements, for example uranium and radium. These very heavy elements have far too many protons to be stable. Therefore, they become stable by emitting an alpha particle, reducing the number of protons by 2. Alpha particles have a large positive charge of +2. This means that they can easily ionize other atoms that they pass, making alpha radiation dangerous to humans. This ionization of other atoms requires energy, so the alpha particles lose their energy rapidly as they travel. This means that they have a range of only a few centimeters in air. They also have very little penetrative force, enabling a sheet of paper to stop the movement of alpha particles. This makes alpha radiation more dangerous to humans if we were to consume a source of alpha radiation, as the alpha particles would not be able to escape the body. The second type of radiation we will look at is beta radiation. As we will look at in a future video, beta decay can happen in one of 2 ways. The first of these is electron emission. This is the form of beta radiation that you will have come across in both P1 and P2. This is where a neutron is converted into a proton and an electron, with the electron being released. For example, the radioactive carbon isotope, carbon-14, decaying into nitrogen-14 and giving off 1 electron. As we can see, one of the neutrons from the carbon has decayed into a proton and an electron has been given off. This leads to a change in the atomic number of the particle. However, it does not lead to a change in the atomic mass. The second type of beta radiation is positron emission, which we will look at in a future video. Beta decay in the form of electron emission has a charge of -1. It has a higher range of movement than the alpha particle, being able to travel several meters, and also has a higher penetrative force, being able to move through paper and thin metal. They are a form of ionizing radiation, however they are less ionizing than alpha radiation. The final type of radiation that you need to know is gamma radiation. Unlike both beta and alpha radiation, which are both particle radiations, gamma radiation is in the form of a ray. As gamma radiation travels as a wave, it is able to travel extremely long distances. It also forms part of the electromagnetic spectrum. And as we can see, it has a very short wavelength, a very high frequency, and very, very high energy. In many ways, gamma radiation can be thought of as being the opposite of the alpha particle, in that it is very weakly ionizing, however can penetrate a long way into materials before interacting with an atom. This means it is able to travel through most materials, however it is able to be stopped by thick concrete or thick lead. Due to lead being able to stop all forms of radiation, it was used to make a radioactive immune plane by the Americans after World War II. The issue with this being that lead is incredibly heavy, and as such the plane was unable to fly. We have looked at the three major types of radiation and looked at their levels of ionization. We will now look at ionization in more detail. So what is ionization? Well, radiation is only dangerous because it ionizes other atoms. In other words, it turns them from atoms into ions by knocking off electrons. This turns them from atoms to a charged ion. Ionizing radiation is emitted by all radioactive sources all the time. It transfers energy to cells in living tissue, causing them to mutate. This mutation happens at the DNA level. This often causes cancer in the cells due to the genetic makeup having been changed. However, we are able to use ionizing radiation in medicine in order to treat several conditions as well as to carry out scans of the body. We will now look at both ionizing and non-ionizing radiation. There are many types of ionizing radiation used in medicine. However, today we will look at the major two. These are X-rays, which are used for medical imagery, and CAT scans, which are used in order to produce an image through the body. An X-ray is a high-energy electromagnetic wave that gets absorbed by very dense material such as bone and metal. This means they can be used by radiographers to take X-ray photographs to diagnose things such as bone fractures. However, due to their ionizing nature, there is a health risk to people who are exposed to them. CAT scans, or computerized axial tomography, use X-rays to produce an image of a two-dimensional slice through the body. The CAT scan uses a large machine, and the entire process can take up to an hour. However, unlike standard X-rays, CAT scans can be used to image soft tissue as well as bones in order to look at organs including the brain as well as ligaments and tendons in the knee or ankle. Just like ionizing radiation, non-ionizing radiation is used in a large number of medical applications. However, we will look at two major types. These are endoscopes, which use visible light, and ultrasound, which uses frequencies above 20 kHz. Endoscopes use visible light in order to look inside the body. They work by using a very long optical fibre which is placed inside the body. The endoscope is inserted into the patient, and a camera on the end of the endoscope can use the light in order to send back an image to a computer. They can be used to investigate problems without the need for invasive surgery, or they can have small tools attached to them in order to carry out keyhole surgery. For example, on a meniscus tear in the knee. We will look at how optical fibres work in a later tutorial video. You should be familiar with ultrasound from both P1 and P2. However, it refers to any frequencies above 20 kHz, which is beyond the normal range of human hearing. Due to using a sound wave, ultrasound is non-ionizing. It has multiple uses in medical physics. However, the main three are the breaking down of kidney stones, which works by concentrating high energy waves on the hard kidney stone, breaking it down into much smaller particles. These particles are then able to pass out of the body in urine, as we looked at in B3 when we looked at osmoregulation. It is a good method because it is relatively painless and the patient does not require surgery. Second major use of ultrasound is in measuring the speed of blood flow. As ultrasound works in real time, it can show the movement and changes that occur in the body. For example, identifying any blockages in the veins and arteries. The final and perhaps most well-known use of ultrasound is in the prenatal scanning of a fetus or a pregnancy scan. As ultrasound is non-ionizing, it can be used to diagnose soft tissue problems and to examine the unborn fetus without hurting it. It works as the ultrasound waves are reflected off the different tissue boundaries as they change from one medium to another. The times and distributions of these echoes are processed by a computer to form the image on the screen. Here is a quick refresher over the radiation uses that we have looked at, including visible light for endoscopes, X-rays in both X-ray imaging and CAT scanners, as well as ultrasound and used in ultrasound scanners and prenatal imaging. However, we have also got gamma rays, which are used in positron emission tomography in order to produce an image. So how can we affect the intensity of radiation? Well, obviously, the intensity of radiation will change as you get further away from the source. If you think about infrared radiation, this makes sense, as you move away from the source of the heat that you feel gradually gets less. This happens due to two reasons. The first is that the radiation spreads out in a circle, and that some of the radiation will be absorbed by the medium that it is travelling through. And generally, the more dense the medium, the more radiation will be absorbed, decreasing the intensity of the radiation. We can use the equation on the next slide in order to calculate the intensity. In order to look at how to calculate intensity, it is important to note that intensity is the power of incident radiation per unit area. As we have looked at, the energy dissipates, so a wave gets weaker the further it travels, assuming the wave comes from a source and travels out equally in all directions. We can use the equation on the screen. This equation states that intensity in watts per meter squared is equal to the power in watts over the area in meter squared. We can rearrange this into the equation on the bottom right, where we have I equals P over 4 pi r squared, which is an inverse square law. However, we can rearrange this equation to make it much simpler to work with. The equation that we looked at was intensity equals power over area. We can rearrange this into a simple triangle, where power goes on the top and intensity and area on the bottom. We will now try a simple calculation. Our question is, the energy from a 100 watt light bulb spreads out over a surface of 2 meters squared. Calculate the intensity of this radiation. The first thing we need to do is work out what the question is asking us for. In this case, it is asking for the intensity. Therefore, we know that the answer will be in watts per meter squared. With this in mind, we know that we will need to find both the power and the area. From the question, we have the power of 100 watts, which is already in watts for us, so we do not need to convert it. And we are also provided with our area of 2 meters squared. Again, this is already in the correct unit. We do not need to convert it. We now have everything we need in order to calculate the answer. We will do intensity equals 100 watts divided by 2 meters squared, which will give us 50 watts per meter squared, which can also be written as 50 watts over meter squared. I will now provide you with 4 intensity calculation questions for you to attempt. Using the intensity equation, calculate the answers to the questions above. If you pause the video now and give yourself 2 minutes per equation calculation. For question 1, we took our 60 watts as our power and our 4 meters squared as our area, divided 60 by 4 to give us our intensity of 15 watts per meter squared. In question 2, we still had watts, so we had our power as 100 watts. However, we were given an area of 5 centimeters squared, which is equal to 0.0005 meters squared, giving us an intensity of 200,000 watts per meter squared. In question 3, once again finding the intensity, we had a power of 1 milliwatt, which is equal to 0.001 watts, as well as an area of 1 millimeter squared. An area of 0.00001 meter squared, giving us a intensity of 1000 watts per meter squared. And finally, for question 4, we were given an intensity of 6 watts per meter squared over an area of 4 meters squared. So we needed to rearrange the equation. In 2, power equals intensity times area, giving us a power of 24 watts. So to look at the topics covered in this first P3 tutorial, we have looked at radiation, looking at alpha, beta and gamma, what we mean by ionization and how to calculate it, what we mean by both ionizing and non-ionizing radiation, and how both ionizing and non-ionizing radiation are used in medicine, including X-rays, CAT scans, endoscopes and ultrasound. In the next video tutorial, we will be looking at the structure of the eye, as well as looking at how we can correct different vision defects.